277 or 208Y120. That system bond jumper stabilizes the system voltage. It's not intended to be sized to carry fault current. It only is employed to use as a connection to stabilize the earth. However, when we get into multiple ended systems, it's very important we focus on these, because most utility transformers are YY transformers, where the XO of the transformer supplying the facility is solidly grounded, and the utility company or your energy service provider will provide a connection between the XO and the earth, grounding conductor or ground grid underneath the slab of their transformers, for this system bond jumper to be connected. You have no control over it. In that case, it's belonged to your utility company, energy service providers. From the supplying transformer, they will bring a neutral conductor and the phase conductors into your service entrance equipment. At that point, inside the service entrance equipment, there is a bond jumper called the main bonding jumper. This bond jumper connects the neutral or the grounded conductor from the supplying transformer to earth. Its principal purpose is to provide a secondary system ground bond jumper in the event the first is lost, but its primary purpose is that it is the main bonding jumper that collects all of the fault current from anywhere in the system into the ground bus or the frame of the service entrance equipment, and provides a routing of that ground fault current to the neutral or the grounded conductor in the service equipment. And it is the neutral or the grounded conductor that provides a path for that low impedance path for that ground fault current to go from the service equipment back to the supplying transformer. If you visualize that motor down in your distribution system having a winding go to ground, the current will go into the frame of the motor, go into its grounding conductor or conduit back to its respective motor control center, from the motor control center either back to the service equipment or back to the dead front switchboard that supplied it. From there, via the conduit or grounding conductor, you go to the ground bus or the frame of the service entrance equipment, and then the current path is via the main bonding jumper that's connected to neutral, and the neutral between the service equipment and the supplying transformer is the ground fault return path to get back to the XO of the transformer to complete the circuit for the energy to flow. That's electricity flows in the circle. That's how that system is designed and intended. Now, the difference, one of the principal differences between the system bond jumper, as I said earlier, the system bond jumper is not sized to carry fault current. The main bonding jumper is sized to carry fault current. As a minimum requirement, that bonding jumper has to be sized at a minimum of 12.5% of the overcurrent or the largest phase conductor. And the reason for that is that that conductor is actually carrying fault current during a phase to ground fault current. If it was undersized, it could actually melt in half. So it has to be large enough to carry the fault current for long enough for the overcurrent protective device to interrupt the fault. It doesn't have to be the same size. However, it does have to be a minimum of 12.5%. I would recommend 20% because over time they can deteriorate or become loose. With a 20% device, you have a larger surface area. Now, how does all of this affect multiple ended systems? In a radial system such that you have one supply and one load, you will have one main bonding jumper and one system bond jumper. However, when you have an alternative power supply, so for example, two sources coming to your building, where your power system is arranged in what they call a main-main configuration, where you have two power sources that are alternating which one is going to be on, and a common bus, and then distribution equipment. The second source provides a means of an alternative power supply in the event that the first power supply is interrupted. That could be the form of another transformer or a generator. Those are the common installations for what is called a main power distribution system. However, Each one of those systems has their own respective system bond jumper and main bonding jumper. That means that downstream of each one, there is a neutral ground bond downstream of each respective circuit breaker. Now, you may ask, why is that important? Let's look at what happens in a radial system if you were to put a ground on a neutral downstream of your main overcurrent protected device or your ground fault protective system. What would happen? If I have a ground fault protection system, they work on the principle of zero sequence relaying, such that all of the currents flowing in the phases equals the current flowing in the neutral. The currents are equal in magnitude and opposite in direction. Now, there is a main bonding jumper that's connected above your sensors. But if I put a bond jumper downstream of my ground fault protection system, then I actually have a path for normal neutral to ground, normal phase to neutral loads to take a circuitous route, and that neutral current can get into the ground plane. That is the number one reason for nuisance tripping on ground fault protection systems, is having objectionable neutral ground bonds. As a matter of fact, it occurs about 70% of the time in our experience. Where a ground fault breaker nuisance trips, the vast majority of the time, is because there are objectionable neutral ground bonds downstream. Now, what the customer does to this is they actually clicks the settings up. This is a bad thing to do. It exposes the systems to damaging arcing ground faults in the system in the future. It also desensitizes the system. The problem with having neutral ground bonds downstream of your sensing elements is that during a time of normal operation where there is no fault, your breakers can actually nuisance trip on a ground fault condition because all of the current that's flowing in the phase is not flowing back in the neutral. Some of it is getting into the ground plane and getting back to the supplying transformer via the main bonding jumper or the system ground jumper. This causes nuisance tripping during normal operation when there is no fault. The other problem with having neutral ground bonds downstream, or what's called objectionable neutral ground bonds, as defined by our NEC Article 250-2, is that during times of actual ground fault condition, your ground fault breaker may not operate at all, because the ground fault current can actually get into the neutral conductor downstream and get back to the supplying transformer via the low impedance path of the neutral conductor, and not get into the supplying transformer via the main bonding jumper. This creates scenarios where the ground fault breaker is not sensing the ground fault. It's not sensing all the current adequately. Specifically, since a person may have played click and pick with the settings to raise the settings up to avoid the nuisance stripping of a breaker during normal operation, what they have inadvertently done is set the settings so high such that during an actual ground fault condition where there are neutral ground bonds downstream, the breaker won't sense the current. So it sits there and cooks, and you have a damaging ground fault condition, which can lead to fire, injury, damage, and death. Now, how does that relate to multiple-ended systems? Well, if you tie two separate power systems together via main system, your neutral conductors inside the switchgear, inside the service entrance equipment, being switchgear or switchboards, are actually tied together. Relative to each other, they have a neutral ground bond downstream of them. That is taken care of by the National Electrical Code that says that if you have objectionable neutral ground currents flowing, then you must take suitable remedial and approved actions. Schneider Electric uses the suitable remedial and approved action by installing a differential ground fault protection system such that there is circulating